Okay, so it's a recording, right? Okay, so so I think I will introduce Chiara. So we are very happy to have Chiara here, who's at Rutgers, and she will speak about their recent work with Angela and I think Nicholas on this geometry properties of sheaves of covariance and conformal blocks. So please.
Thank you for the introduction. I hope you can all hear me. And
yes.
Yeah, so today I will talk about some essentially geometric properties of sheaves of coinvariants and conformal block. And this is based on some, say, joint work with Angela Gibney and Nicola Tarasca. These would be sort of the basic properties. Oh, I cannot write. But actually the geometric properties, it's really a joint work only with Angela Gibney. So what we are going to see today is, as I said, as the title says, we have some sheaves over the moduli space of curves of fixed genus and mark points. And as an algebraic geometer, I'm interested inside this space. And a way to study this space is to study bundles or sheaves of on this space. And I will say a bit more about this later. And a way to produce bundles is to start with some representation theoretical input, which is, in this case, modules over a vertex operator algebra of co-FT type. I will say in a second what I mean by this. But the main idea is that essentially every time I fix a curve and enough points, and I fix a vertex algebra and enough representations, and the idea is that if I have n points, I have n modules, then I can cook up a vector space, which if I vary see the curve and the points in this moduli space of curves, fit together to define a sheaf. And the idea is that under certain conditions, these sheaves are vector bundles. And we know that vector bundles, when they are nice enough, and this is where the geometric properties will come, will allow us to define maps between this variety and projective spaces. And so we can have more information about this projective space. So the goal of today will sort of try to explain to you why what these objects are. So I will start maybe with some definitions and maybe really explain better what is the setting that I'm working with. And so this is the first part, just the intro. And the second part, we really are going to talk about these geometric properties, which for us today just means global generation. And if you don't know what this means, it's okay. We're going to talk about this later. And the interesting thing, as a preview, we know that we can construct sheaves of this type, which are called coinvariants, started with representations of Lie algebras. These are just a case, sort of subset of this case. But somehow in this more general setting, where instead of just taking representations of Lie algebra, we start with representations of vertex algebras, some new phenomenon appear. And so I will explain to you, I will give you some counterexample and state a theorem that we proved with Angela Gibney and some ongoing work. And I will probably at the end have some questions for the experts on vertex operator algebras. So let's start with the setting. And I want to apologize if I forget to mention, to give credit to people, because as you all know, I'm learning these things, and I hope I will not forget to address who proved what and when. Please interrupt me if you want to add some comments on that. So first of all, what is a vertex operator algebra of co-FT type? So let's start with the basic properties. So we start with a vector space. which I want to be graded, and it's graded by the non-negative integers. And I assume that there is a preferred element in degree 0, which actually spans all the degree 0 all the degree 0 vector space graded component. I further assume, and as you will see here, some of these conditions will actually be redundant, but I just want to just write down all the things I need, even if there might be some implications between them. All the graded pieces are finite dimensional. And so far, this will be just a vector space. And to be a vertex algebra, I need to have a way to have a state field correspondence. What it means is that if I take an element of V, so a vector, I want to associate a family of endomorphisms of V. And the way in which it's done is to really associate this series and its field, because I know that if I call this Y of A, we know that YA of B belongs to, it's really a field. So the poles are bounded. And of course, there are many, many axioms to, well, some axioms which describe the interaction between, like some weak commutativity and associativity of this, of Y, of the morphisms Y. And I think that I really need for some properties that we really need to do geometry is a conformal structure. So the conformal structure is, well, I want to have a vector in degree 2, which is the conformal vector, which gives us the conformal structure, meaning that if I take this set of endomorphism, where omega n is just the endomorphism, which is induced by Y and omega, then there will exist a coefficient, so that called central charge, so that this group of endomorphisms is Lie algebra of endomorphism is isomorphic to the Wirsor Lie algebra. And for the construction of these sheaves that I mentioned before, I will not use the C2 cofiniteness condition and rationality, but I will actually need them to have properties of these spaces. So I will, let's say, we are not going to see where these two conditions will play a role at the moment. Maybe we'll say a couple of words, but the cofiniteness condition tell us that V modulo C2V is finite, where C2 of V is the space generated by elements of this type. And the rationality condition, so C2 cofiniteness is sort of an intrinsic condition, while the rationality condition has to do with the category of representations of V modules. So rational just means that the category of representations is semi-simple. So if you want to describe it through the Jou algebra, this will tell us that the Jou algebra is a semi-simple algebra. So right, and in particular, we're going to have also the main thing that it's interesting for us is that there are only finitely many simple modules for V. Now, I have said modules, but I didn't say what modules are, what I mean by modules. And I think in general, there are different definitions of modules. So let me now explain or try to set up the notation for what I mean by modules, unless there are questions at the moment. Okay, so what do I mean by modules? Similarly to the vertex algebra V, a module over V is a graded vector space which receives an action of V, but the action is again induced by families of endomorphism. And I assume that this vector space is graded with lowest degree being in degree 0, and I assume this to not be 0 at the empty set. It's just there will be at least an element in W0. And again, I have a conformal structure, and I know how the action of the element A, since if I take a homogeneous element, I know how it acts on each component. And this is sometimes called the admissibility condition on the modules. And we further know that if the module is simple, and I'm always assuming V being C2 cofinite and rational, that actually the operator L0, which is the action, so L0 is an element of the VR0, which acts on W through the conformal structure given here, is an action by multiplication by the degree, and constant, which is called sometimes, it's one of their names is the conformal dimension, which we know being in a rational number. And also, let me mention, I didn't mention before, but also the central charge CV, I want to use some terminology, is also a rational number in this case, and it's the same central charge that we had for V. So the VR0, there is a compatibility. I want my conformal structure of V and the conformal structure on modules W to be compatible. And I didn't mention this, but of course we have, again, axioms which control the interaction between let's say Y and YW, and between also the action of the VR0. So this is sort of what I mean by V modules. And so the first step in this talk would be, how can I construct then spaces which
I'm sorry. So I think the last line in your here, I think the W so W is simple. Okay, so sorry. Yeah. So
yeah. Sorry, maybe I didn't emphasize it. So this is not, if W is not simple, then you don't have AW. But I mean, yeah. So we need the simplicity, and we are going to actually, for what we're going to see today, we will only consider simple modules. Thank you for the reminding this. Yeah, so what I want to describe today is how to construct what I call the spaces of coinvariant, which depends on a vertex operator algebra of T type module, and C will be a curve. Let me just draw it as a Riemann surface for simplicity. It can be also, it could be nodal, but I put a picture. Let me just not do it. And I fix a point P in the curve. Okay, so this is my curve, this is the point. And how can I construct this space? Well, the idea is that I would like the space of coinvariants as being a quotient of W by a Lie algebra encoding the geometrical input. And why do we want to construct this? Well, in the case of Lie algebras, meaning where my vertex algebra is the algebra associated with simple Lie algebra G and of level L, and I always assume L to be a positive integer. Then we know then a way to construct conformal blocks, to construct invariants, is to take the representation W and quotienting out by the action that this Lie algebra has on W. Where this Lie algebra here, it's essentially I'm extending the scalar of G with the functions of the curve minus the point. And the reason why this acts on W is because naturally W is a module for what I want to call the affine Lie algebra G hat, which is a central extension of G. And essentially, it's sort of an algebra which I want to see living near the point. And so this algebra lives there because there is a natural map of the algebra given by the residues from this algebra to here. So essentially, in the Lie algebras case, which were studied by Tsushia, Ueno, and Yamada, for instance, not using the language of vertex operator algebra, but just using the languages of affine Lie algebras, we had these descriptions. And so the idea is that, can we do the same thing for when the vertex algebra is maybe more complicated? Maybe there is not really a Lie algebra underlying this. There is, and the answer is yes, we can do this. So the first step is to construct a Lie algebra which acts on W. And so I'm trying to go a bit fast here because this is not the main the topic of today's talk, but feel free to interrupt me if something is not clear. So the first step would be to construct a Lie algebra encoding the geometry and acting on W. And the key input here is to use really the conformal structure on V, because using the conformal structure on V, we can construct actually a sheaf of vertex algebra. So sort of a vertex algebra, but in a sheaf way. So it varying the point. And this is further equipped with a connection. And why is this important? Well, because we can construct this Lie algebra, meaning I can take the quotient, and I'll explain in a second how this looks like near the point P. So I can take the quotient of V tensor omega by nabla V, and I take the section over C minus P. And let me remind you that we could have also, and I think in one of the previous talks of Lingui, he was not considering the quotient. We could also not consider the quotient. It will still be a Lie algebra, just that the action on W factors through the quotient. So we can as well take the quotient. But I know that sort of well-defined, everything which is in the quotient acts trivially. And so going backward, every element of this space, I just take essentially, this operation is take its expansion at the point P. I rewrite this function, I take its Laurent series, and I see how it acts. And so, well, we sort of have an action. And so we sort of have coinvariants. But you can see here, we actually had to use coordinates. So in order to define this action, we actually use coordinates at the point P. And so this would be a coordinate, sort of, this would be, if you want a local picture, the local definition of these spaces. And so what we're left to do is to sort of forget the coordinate. And the way in which I like to think about forgetting coordinates in this context is to imagine that this space here, so this sheaf of coinvariants, is attached to a curve, a point, and a coordinate. And I would like to forget the coordinate at the point and just consider just the curve and the point. And so if I think it in a geometric sense, it's like taking a point. I would like to have something, the modular space of curves just of genus G with one fixed point. But I actually was, if you want, in a modular space parameterizing curve, point, and coordinates. But I'm in good shape because this is a torsor. It's a principal bundle by an int group, and I can just apply descent. So this is a torsor along, I call the group O to O. It's the group of the changes coordinates. And so I can essentially apply descent and obtain this space which depends on the curve and on the point and not anymore on the coordinates. And the idea is that I could write this procedure with, and let me maybe choose another color, having more points, and I put a bullet there, and more modules. And essentially the idea is that if I have more modules, I just take their tensor product and I remove all the points, and the constructions are similarly. Of course, here I will have an O to the n. So it's the same idea, I just have more insertions. And so this is how this vector space is constructed. And now, and the idea is that varying, if I vary the curve into this modular space, these spaces together, these spaces fit together in a nice way. So they define a sheaf. But let me tell you now the properties of this in the next slide, unless there are comments or questions on this. Maybe I just want to say this construction is something that was, of course, very well known for genus 0 and genus 1. For genus 0, very well known also over MGN without the points, or just known. I don't know if it's very well known, but but I don't know if it was constructed over MGN bar in this generality before Angela, Nicole, and I and our work for higher genus. So this is something that I don't know. I think this is nice. And okay, so let's maybe start with some properties. And I just put here the names of myself and my collaborators, Angela Ghibli and Nicola Tarasca, because some of these properties, most of them we just put them in some papers we've written together. And for the constructions, we actually didn't need the modules to be simple or V to be C2 cofinite or rational. But I will just stick to this. But for the properties, I will need these conditions. So let's assume them. And under this assumption, we have the first result is that actually these spaces fit together to define a sheaf over MGN bar, where I sort of substitute, I don't write anymore the curve, but I just remember the genus of the curve, since they live over MGN bar.
Sorry,
and yeah.
I just have one question. So the cohomology FT type means the whatever the definition you gave before, right?
Yeah.
Okay, so what this COH means, the cohomology?
Yeah, so we're gonna see in a couple of points that their Chern classes defines a cohomological field theory. So this will be the initial of cohomological field theory.
Okay, so but you do not have like an extra operator which should give you some kind of a fermionic thing or something.
What do you mean by that?
So, but mainly it's because I myself actually has some kind of a paper on so-called topological vertex algebra. There's some extra things so that you can get a cohomology with respect to some complex. But anyways, I just want to see whether your definition of vertex algebra has this type of thing or not. I do not see that in your description. You have that, right?
Yeah. So maybe when I go to in a couple of bullet points, I will say something about what they mean by cohomological field theory, and we can see whether we agree on something or not. Or probably I will learn something new. Yeah. Okay, so this result here is that which should be a theorem, but I just list these properties because it's not the main result of the day. Tells us that these spaces don't fit together just as a sheaf without properties or sheaf of modules, but actually they define a vector bundles of finite rank. So if these two important properties, so one of these is that they are finite dimensional, which a priori by the definition they are not, because I just take an infinite dimensional vector space and I quotient out by some other probably infinite dimensional vector space. Nothing tells me or guarantees that it's finite dimensional. And more importantly, they are locally free. So they are really vector bundles. And the interesting thing is that this is crucial because if I have a vector bundle, I can always compute for study MGN bar, I can always compute the associated determinant, which is a line bundle. And we can find a lot of information about the moduli space MGN bar through these vector bundles. In general, they are just objects which behave better than just quasi-coherent sheaves. So now let me just say a couple of words on why these two properties hold. So the first one is the finite dimensionality. And a key ingredient that we have used to show finite dimensionality is the C2 cofiniteness condition. And our proof is actually based on proof of actually Abeng and Nagatomo, although he uses a different coinvariant. So the Lie algebra that they use to define the coinvariance is slightly different. They give rise to the same coinvariance, but it's not obvious maybe on the nose they are the same. And so the C2 cofiniteness guarantees that these spaces are finite dimensional. The fact that actually they are vector bundles, well, it's sort of a consequence of the Sowing theorem, which is a refined version of factorization rules, which essentially tell us that we can understand the behavior of these shifts over a nodal curve, of the space over a nodal curve, using the behavior of the normalization. And actually, we can be a bit more refined, saying that if I want to understand the space of coinvariants, where instead of having a nodal curve, I have a family over a one-dimensional, over a disk, essentially, C of tau, then this is related to the conformal blocks, sorry, the coinvariance over just the node tensor with tau. And then again, I can relate it to V of the normalization tau. So the Sowing theorem essentially gives us more like a family version of the factorization rules. And we have proven it in algebraic method. And here we really need both. So we need, first of all, that they are finite dimensionality to conclude the factorization rules, and we need rationality to state also the precise theorem, which I will not say today, but it's sort of essential for the proof that they are finite dimension, they are vector bundles. And a crucial ingredient is the fact that these spaces are actually equipped with a projective connection on MGN. And actually, you can describe also how the connection is on the boundary. There are some logarithmic singularities there. But essentially, let me say that these two conditions together, if you want A and C, are enough to guarantee that these coinvariants are a vector bundle of finite rank over the open moduli space where we only have smooth curves. And this together with B, we say, okay, the result is true also over the closure, so also on the boundary. So this is some sort of properties which are essentially like, for example, factorization rules is fundamental to compute the dimension of this space, and so gives the Verlinde formula that we all of us, or many of us, know what it is and the importance that this has had. And before going to the property I want to discuss today, let me mention, maybe going back to his questions, the co-FT. So what I mean by homological field theory is that I always have, so if I can take the assignment, we take a genus, a positive integer, and n modules, simple modules, and I associate the Chern character. So this defines a simple co-FT. This just means that the way in which what I want to say about it today is that we can explicitly compute Chern classes of these bundles, so we can really have a control of the degree of these modules, whether they are positive, negative, and over, and so really understand the properties through this thing. And actually, this coFT really comes from the underlying topological quantum field theory.
So I think, is it possible that this, because cohomology field theory will give us a topological field theory. So is this the corresponding to the related to the three-dimensional topological field theory? Do you think?
Yes. So it is. So a fundamental input for this. So it gives rise to the, sorry, it is related to the topological field theory. And once we know what happens on P1 with 3 points, we know everything essentially.
Yeah. So actually,
this is what you were.
Yeah. Actually, what I want to know is that because if there is a cohomology field theory, means that you have some kind of a complex, right? Because it's a cohomological. So then you see, you can take the cohomology. The cohomology is supposed to be a topological field theory. So do you know what that is? Roughly speaking.
So what I think I don't fully understand the question. So what I know is that when I say character, so to me say cohomology, because this lives in the cohomology ring, in the rational cohomology of MGN bar. So this is an element in the rational cohomology. Okay, and so if it was just TQFT, then of course this will just go down to the, will just be just positive integers or 0 as well.
Yeah, no, I'm just trying to see, what do you mean by the cohomological field theory here?
Okay, so what I mean is that I need to have, so I have a map from, so I first of all have a finite set. I have, let me call curly W. I take, this is the space of simple representation. In this case of V, this is a finite set, which has also, and I can also associate, every time I have W, I can take the contra gradient. So I have a duality. And if I have a space with this property, then if I can, an association of this type defines a semi-simple coFT if propagation of vacua holds, which we have. I didn't mention it here for just space reasons. Essentially, factorization holds, and with the fusion rules, if I have control of what happens on P1, this is what I need. Yeah.
Okay. I mean, so I think that see, I tried to figure out what you mean, but I think that this is probably related to the topological field theory, right?
It is. It's actually determined by the underlying topological field theory because since it's semi-simple, the classification of Giventhal and Telemann tell us that they are uniquely determined by their the underlying topological field theory, which then can be further described with this twisted module structure using the Atiyah algebras.
Okay.
Yeah. So it's really somehow, let's say, the way in which we can describe it through this and the reconstruction theorem really boils down to knowing the TQFT. But a priori, sorry if that was confusing, but I hope it's clear. Maybe we can talk more about this. I'd be happy to learn more about that. Okay, so now one property. So let me maybe erase this just because I need a little bit of space down here. So all these properties here are known for, let me say, when we start with the vertex algebra associated with the finite algebra of positive level. But there are some other properties that we know being true in this case and had been useful for algebraic geometers. one of these properties that I will not mention today, I will not discuss about it today, but I'd like to understand whether it's possible to generalize, is the relation of conformal blocks with theta functions, meaning there is some sort of modular interpretation. If I take the conformal blocks, which means the dual of coinvariants, this naturally describes global section on a moduli space. But the second property I want to discuss today is the fact that if I am on genus 0, if I am over the moduli space of rational curves, and I take some modules here, this vector space is always globally generated. It could be that this module is just 0, so there is nothing more to say, but it's independently what the WIs are, this is always globally generated for this vertex algebra. And so it was natural to think as an algebraic geometer, oh, can we sort of describe this property in this case? And so before doing this, let me tell you what global generation means, and then why we care about it. So first of all, every time we have a vector bundle on a variety or a sheaf, but let's just stick with vector bundles, we say that it's generated if it's a quotient of a constant sheaf, meaning there is essentially a vector space and a surjective map between this constant sheaf and V. And it is important because if V is globally generated, then it means that the line bundle associated defines maps from this variety M to an appropriate vector projective space. And many works of Angela and collaborators were destined into understanding how can we find properties of MG and bar, or M0 and bar, but mainly MG and bar, knowing maps which this space admits. So in general, if I want to study an object, very often in algebraic geometry, it's hard to study the object itself. It's easy to describe the set of maps admitted by them. And very often these maps are essentially constructed from line bundles, base point free line bundles. And so it's interesting for us to understand, can we have actually so many more maps? Can we construct this? Because if all these bundles are globally generated, it means we will have so many more maps, and maybe we find more, we can just say much more, have more information about the MG and bar, which although it's a classical object, there are still many questions to answer about it. So as I mentioned before, Fakhrudin, which actually also I think work based on some work of Ueno, shows that these sheaves of coinvariants are globally generated because they are quotient of the 0th degree part. So we can take as P just this tensor product, just the 0th part, make it become a vector bundle, which is trivial. And this naturally maps to the coinvariants, and this map is further surjective. So we thought, okay, maybe this is true in general. Well, one theorem that we have at the moment is that this is true under the assumption, of course, I assume that the modules are simple, V of coef T type. I'm always in the assumption so that these objects make sense. Under the assumptions that V is strongly generated in degree 1. This condition means that essentially I can write every element of V as a combination of elements of the form of this form. Right, so every element of V is essentially a combination, a linear combination of elements of this type, where the A, I, J are degree 1, and the element Jn are in Z. So essentially, V1 generates everything. And one can think, are we sort of Okay, so is it true that this theorem, that actually the Fakhrudin's theorem holds in general, and is just a step towards that? Well, no, we actually found some counterexample since we found some vertex algebras of QFT type and some modules where the associated sheaves of coinvariants are not globally generated. And before going to the proof of the theorem that Angela, Gibney, and I have proved, and this is in a work in progress, so there is no archive preprint yet, but I can tell you about the proof later. Before that, I'd like you to show the examples that tell us that, okay, this theorem of Fakhrudin cannot just be simply generated, generalized, substituting this vertex algebra with any other vertex algebra. This will not be true. So, okay, so the first example takes the Virasoro. I take the reducible, how do you call it? The discrete series associated with of weight 0 and central charge 1/2. And we know that there are only 3 representations, the trivial one and the ones associated with weights 1/2 and 1/16. And we also know all the fusion rules. So we know everything about vertex, the acidic conformal blocks. We know how to work with the coinvariants explicitly. So this was a very good place where to start thinking about examples. So the first thing is that if we just start on M04, so this is just P1, there are only 3 sheaves of coinvariants where the degree is different from 0. So if the degree is 0, then there is really not much we can do. So there are only 3 sheaves with degree different from 0. And these 3 sheaves are the ones where the insertions have to be looked by a combination of these 2 modules. And they need to be an even combination of the 2, otherwise they are just going to be of rank 0. So one of them has, where the insertion is all of weight 1/2, have rank 1, degree 2, having degree positive. So in this case, I forgot to mention that on M04 bar, degree positive is the same as being, well, let's say if you have a line degree positive and you have a line bundle, it means that you are globally generated. But as soon as we hit a negative degree, this will be a disaster. So if the degree will be negative, it means it's not globally generated. So far we are not in a counterexample. The next sheaf also is not a counterexample, but this last one, when I have 1/16 in all the points, it is a rank 2 and it is negative degree. So this is not globally generated. And so we thought, when we saw this, we thought, okay, maybe it's the rank the problem. It's too much. Maybe, rank equals 1. Maybe that would be enough. Well, no, that is also not working. Not entirely, because we can construct an example through the lattices. So I can take an even lattice. In this case, it's just generated by 1 element, and the pairing is 8. It's an even lattice. We know the representations are given by just the dual lattice modulo L itself, which is just Z modulo 8Z. And so I will index the representation with integers from 0 to 7. We also know the fusion rules, of course, by works of people who are present in this room. And we can know that, again, on M0 and bar, M04 bar, when I insert W2 4 times, it's the line bundle. The rank is 2. The rank is 1, excuse me. But it's not globally generated again. And the reason why it's not globally generated, the way in which we can compute this, I can compute the first term class. This can be, it's just a homological class, which you can interpret all these elements. Essentially, this is among P1. These can also be, essentially, they are points. So to compute the degree of this bundle, I essentially forget all the symbols that I put here just to be precise. And I obtain these formulas, which gives us that the degree is -2. Now observe that these numbers here, so these numbers here that I put here, these are the conformal dimension of W2. And this 16/16, this is the conformal dimension of W4. And where W4 exists, well, if I have a curve comes from the diffusion rules, where if I have 2 points where the representation is acidity 2 and 2, on the third point, I need to put representation 4, otherwise I will have a 0. I will not have anything of rank. I will have rank 0. And so here we have the this line bundle is rank 1, but you still have some negativity. And actually you can do the same thing. Every time your form is actually 2 times 2 times k, you can always have the insertion wk 4 times. Let me just write here. So if you have wk, and the solution will be -k. So you already have a family of lattices which have this, and the line bundles, I believe they are all line bundles, but you always have line bundles on G0 for lattices, so it's not a special case for M04 bar, but the degree is negative. And so here we see that it's not enough to have rank 0, rank 1, but there is a difference between the Virasoro and the lattice. So one of the difference is that, if I believe correctly, is that the lattice, the Jou algebra of the Virasoro is a billion. And so this means that the W0, so every time you have a representation, W0 is one-dimensional. The minimum degree is one-dimensional. Here, this is not the case. I think for lattices, and this is where we would like to have your help to be sure.
Help with this.
Yeah, we'd like to find a way how to compute the dimension of W0 for every dimension. And for lattices, I believe it's not at least not for W2 should not be one-dimensional.
Do you agree?
So if I take W2 0.
No, I switch that upper 2, lower 0.
Oh, but it's W2
just
0.
Yeah, good.
So the dimensions here, it should be bigger than 1.
Do you agree?
We can talk about this more.
Yeah,
but
we'll talk about it in the future. We need to learn how to compute the dimensions of the 0 degree component of the modules. Maybe Jason.
So this is basically the lowest weight space.
Yes, we need to know the dimension. We need to
the lowest weight, yeah.
We just need a tutorial on how to, figure out I mean, we know if the Jou algebra is commutative, that's great, but we need another way to compute those dimensions.
And anyhow, okay, so this is just a preview for, we are gonna say something about this a bit more later, but maybe in the last minutes that are left, I want to say a couple of words about the proof of the theorem I stated before. So I copied back the theorem, so we know where we are. And I first want to say, okay, what is the setting? Let's try to prove this theorem. So what do we know without even thinking about the assumption of strongly generated in degree 1 or the fact that we are in genus 0? So what do we know? So the first thing is that this map, the map between this constant sheaf and this vector bundle, is always defined, even for higher genus. I'm sorry, I wrote here 0, but also for higher genus, this is true. And this is, excuse me, and this is always defined because the idea is that if I think about what happened on M, G, and triangle, meaning where I fix the coordinates, so with coordinates, the way in which we have defined this space was really a quotient. Now let me just write bullet instead of the product of the W's. So we know that the over, if I fix coordinates, the sheaf of coinvariants is a quotient of this space, and this admits a map from this bundle. So here it's like below I write, okay, if I fix coordinates. But what I know is that, well, the way in which to go to the real coinvariance is by descent, forgetting coordinates. And this procedure of forgetting coordinates, essentially, since we are in the lowest degree possible, it doesn't do anything here. So it means that this really descends to the constant bundle too. However, notice this does not descend on the constant bundle. This will descend to some ugly thing, to something which is not constant. So we still have this map, if you want, but this thing, it's just ugly. So we cannot just say, oh, it was a quotient above when I fix coordinates. It's a quotient after when I forget the coordinates. Well, it's a quotient, but it's not a quotient of a constant thing in general. So, but this map is always defined, not necessarily because the genus is 0 or because our vertex algebra is strongly generated in degree 1. So once we have this map, which is a global map, so we have a global map. Now to check that it's surjective, it's a local matter. So to check surjectivity is a local matter. And now we can go back and choosing coordinates. Just to, so we can really reduce to show that this map is surjective by say, okay, I can now take, first of all, I can, instead of considering this sheaf of coinvariants, I take the space, I have to take every possible curve of genus G with the points, and I can even fix coordinates. And I need to show that this map, which is the composition, it's surjective. Okay, and how do we do this? Well, it's natural to use to show this using induction, if you want, on degree. What do I mean by that? Well, if I want to show that this map is surjective, it's enough to say that if I take an element, let me say, if I take a homogeneous element, maybe the degree is D inside this tensor product. If I show that every element of this is written as a element of, or sum of elements of lower degree plus something that goes to 0, meaning something which belongs to the image of the algebra, then I'm done, because I can keep applying this procedure until I go back to degree 0. Right, so this is something that, okay, so we would like to do this. And to do really this step, this is where we use both the conditions of being strongly generated in degree 1 and the genus 0. So, and on the slides, let me maybe have this both together, since I don't have that much time. So the fact that we have the vertex algebra is strongly generated in degree 1 tells us that the element, we said I start with an element of a certain degree, and I want to write it down as an element of degree less than itself, plus something that was sent to 0 in the coinvariance. It means that if I write it as a tensor, well, maybe one of these elements, I call Wi, can actually be written in this form, where the Ui has lower degree, and A has dimension as degree 1, and J is positive. So this doesn't maybe follow automatically from the strongly generated in degree 1 from the definition, but essentially using a bit of commutators and associators, you can just deduce that this is true. And the genus 0 allow us to essentially, I like to see it as I can sort of lift A minus J. I take this element and I sort of lift it to really an element in this Lie algebra, in this chiral Lie algebra. meaning that I can always construct an element here so that its action on the point I, where this wi is really given by a minus j and lower degree terms, while the action on the other points, well, it's less or equal than degree of a minus 1. But remember, a had degree 1, and so it's actually less or equal than 0. So the genus 0 essentially stops here. And of course, we need the strongly finitely generated to say, oh, this actually the degree is less than 0, less or equal than 0 for the other points. And these two conditions together really allow us to conclude that if we take the element W that we started with and we subtract the image of these other elements, where essentially instead of Wi, we plug in Ui, then this element here has degree strictly less than degree I started with. And so we are done by sort of induction on degree, as I said before. And okay, so this is the idea of the proof behind it. And so let me just conclude saying that work in progress with Angela, it really has quasi-theorem, because we are checking out the details, is that if we know that the dimension of the lowest weight component of the modules is 1, and if we know that the rank also of the coinvariance is 1, then we can show it's globally generated. So it's not true that one of them is enough, only one of them, but together they give a lot of constraint. And observe that this just means that our map, we are left to prove that this map to the coinvariance, like this, is a non-zero map, right? They both have dimension 1. If I want to show its objective, it's enough to show that it is non-zero. But yeah, so this is something that we are polishing, and it's something that we would like to understand is really how to ensure this condition beyond, you know, we know that if the Jou algebra, if the Jou algebra is commutative, then we already have that condition. But can we actually compute this dimension? Is there sort of a condition that clearly identifies all those modules with this property, besides saying the dimension is 1? And so this is something I would like to discuss with you. But I think my time is up. So I think I just thank you.
Thank you. So any questions? Yeah, I have one question. So the one of the main assumption in your theorem, last theorem, is that it's a strongly generated by weight 1 element, right? So the degree 1 is essentially weight 1, right?
Degree. So what I say degree 1 means that it lives in weight 1. Yeah.
Yeah, weight 1. So then see essentially this is alpha Lie algebra, right?
Right,
It's a product. It's a tensor product.
Yeah, it's because the weight 1 give us a Lie algebra, and then the vertex operator.
We don't know that the Chern classes of the vector bundles generated by vertex algebras that are tensor products of affine Lie algebras for different Lie algebras and levels. We don't know how those relate to the Chern classes of the individuals. So it's really a new bundle for us.
Yeah. Sorry, I forgot. Yeah. So.
Yeah, but you're right.
It's evidence that it sort of makes sense that it's right, because we know it was right for affine Lie algebra, and these are essentially products of tensor. The vertex algebra is a tensor product of them. But yeah, so from a geometric point of view, it's a bit obscure why this should be the relations between them.
So it seems that you're saying that one of the obstruction to general case is whether this lowest weight space dimension is equal to 1 or not, right?
Yeah.
Okay, so but
to go through this proof
Mhm.
to use this induction method. Yes.
Uh-huh.
Because this induction method is essentially, if I know this, and
Uh-huh.
the idea is really similar to what Ueno does, is I can always rewrite one of these elements as just something times something of degree less, and this starts
Right.
doing the induction.
Right.
And we can do this, but then if we don't have degree 1, then we cannot conclude the induction.
Uh-huh. Yeah, so for me, the main thing is that even for affine Lie algebra, I think the lowest weight space, the dimension in general is not equal to 1, right?
Oh, yeah,
Because
V1. Oh,
the lowest weight space
no,
for
they
affine Lie
will,
algebra.
no, because these
general.
will be the representations of the affine Lie algebra, so they are not 1.
Yeah, so the yeah, for like the minimum model or something, so because the irreducible module can be generated by one element, so
Yeah.
it is.
But it's interesting how the problem is that we have these two conditions, and it could be that maybe this is 1, but the rank is too big, and if the rank is too big, then of course you don't have a surjection, right? Because if this is too big, and the problem is that it's not clear how, I mean, there might be another vector space, another trivial space which surjects, but it's just very hard to find one. And so this is sort of the natural candidate.
Right, and we're using Jou's theorem, right? That
Okay.
everything is generated over the degree
Okay.
0 part.
I see.
Yeah, but
okay.
So it's just these two conditions together. You know, we can say GeoAlgebra is working here, like for the Virasoro, but then the ranks might just jump.
We also see a lot of examples when we see some examples when the bundle has rank 1 and the sum of the conformal weights is an integer.
But that, yeah, we thought that was an option, but then the lattice again proves a counterexample.
But that's not. But when the dimension of the lowest weight is 1.
Yeah, that is true. This is something that we notice in the Virasoro. There is this sort of relationship that if the sum of the conformal dimension was 1, then suddenly things look well. So it looks, I don't know, it looks like sometimes with this numerical evidence, and this is so, I find it having the CoFT, the fusion rules, the factorization, so everything sort of allow us to actually explore. And I hope someone will be able to code things. I think it would be nice if someone can actually write a program where I gave them my CoFT type as an input, and I tell them, take this vertex algebra. These are the fusion rules. These are the central charges. This is the central charge, and these are the conformal dimension. Tell me